Hello, this is Mr. McMurray, and we are going with the flow today because we're talking about fluids and fluid mechanics for Chapter 8. All right, fluids are any material that flows. And normally, if we were talking about fluids, like say bodily fluids, we'd be talking about blood, spit, mucus, whatever, any type of liquidy type fluid that's in your body. Okay, and we tend to think of fluids. Are you drinking enough fluids? Well, are you drinking enough liquids? But in physics, a fluid is anything that can flow. Okay, a solid cannot flow. Okay, it keeps a certain shape and doesn't flow. A liquid obviously can flow and change its shape. If you pour a liquid into a cup, it takes the shape of that cup and it flows into that cup. But also gases flow. Okay, and so gases are considered to be fluids. So when we talk about fluid mechanics, we're really talking about air and water, or gases and liquids. Okay, it doesn't include solids, but it does include both liquids and gases. Unlike when we normally say a fluid, we just mean a liquid. If it can go with the flow, it's a fluid. All right. Now, one of the first characteristics we want to talk about is density. Okay, for example, let's say I have a loaf of bread. All right, and when I'm loading it, I make a mistake and I put groceries up on top of the bread and I squish it flat. Okay, now, is there any more or less bread than there was before I squished it flat? And the correct answer for that is no. Okay, there's still the same amount of bread, but obviously something's changed. If I try to make a sandwich with this bread, it's not the same as it was before. So the question is, what has changed? Well, is there any change in the mass? Well, what is mass? Mass is how much there is, how much matter makes up the bread, and basically there's still as many atoms of bread as there was before. But what has changed is the volume, or the amount of space it takes up. Okay, it used to come up here and take up this amount of space. Now it's been squished into a smaller amount of space, and so that is its volume. Its volume has been decreased. Okay, so to show this change, that it has the same mass but the volume is different, we measure that in a quantity known as density. All right, you've probably heard about this in all your classes, hopefully in school. Not a new concept, but just to go over it real quick. Your density is equal to the mass, how much matter there is in something, divided by the volume, or how much space it takes up. All right, the higher your density, that means you have a lot of mass in a small amount of space. All right, if you have a small amount of mass and a large amount of space, then you would have a very low density. So as the mass increases, you would have more density. As the volume increases, you would have less density. All right. So for example, you could have let's just say you have 50 grams of air and you have 50 grams of water. Their mass would be the same, but the water would take a relatively small space, whereas the air might cover up a big volume, okay, because it's not very dense. So we would say that water has a higher density than the air because the same amount of mass takes a lot more volume in the case of the air. Now, if we were to write that in symbols, same thing, density is equal to mass divided by volume, just a little m over v. Now, just some comparison, for example, we say water would have a volume of 1 gram per milliliter. You may see that with a big L or a little l, but either way, 1 gram per milliliter. In other words, 1 gram of water takes exactly the volume of 1 milliliter, which is about the size of a dice. If you were one of a pair of dice, if you were rolling dice, they're a little bit bigger than that, so it'd be kind of like a really small dice, but a little smaller than usual dice. But that's basically what it was. That much water would take 1 milliliter. Now, it turns out that is not a coincidence that water is exactly 1 gram per milliliter, because when they did volume, originally they did length times width times height, okay? And so the amount of water would be 1 gram of water is equal to 1 cubic centimeter. Okay, which is 1 centimeter times 1 centimeter times 1 centimeter. That's where we get our 1 centimeter cube, which would be about, like I said, the size of a die. Okay, like so. We'll just put a dot on it because I don't have time to draw 6. So that's our die. Okay, so that would basically be 1 gram per cubic centimeter. But they said that doesn't really work for liquid because you don't usually have length times width times height for a liquid. So when we measure, like in a graduated cylinder, we pour water in there, they said let's make 1 milliliter equal to 1 cubic centimeter, and that way it will also be 1. So if you see water in milliliters, if you measure out 50 milliliters of water, you know that you have 50 cubic centimeters of water, or you may hear cc's, like on medical shows, so many cc's of something, that's cubic centimeters. It's another way of writing it. Instead of cm to the third, you can just put cc for cubic centimeters. And you would also know that if you say had 30 milliliters, you would have 30 grams of water. So that makes it very handy because we don't have to measure out the amount of water. To find its mass, we know what its mass and volume would be. Now, just for comparison to other substances, ice would have a density of 0.92, which means it's less than 1, which means it's less dense, and that's why if you put ice in water, it's going to float. Also, alcohols tend to be less than. So if you gently poured alcohol into a container of water, okay, it has a density of 0.81. This is ethyl alcohol. Then it would float on top. Now, if you were stirred up, it would mix together. And so, look, for example, like when you have rubbing alcohol, that's alcohol and water mixed together. But if you gently poured the alcohol into the water, it would just float up on the top of it. Okay. Now, other things have heavier than that. We tend to think of lead as being very heavy and very dense, and it is. If you feel lead weight or something, it feels fairly heavy. It has a density of 11.3, which means for the same volume, or for the same mass of lead, it would have a mass 11 times stronger or heavier than water. Mercury is 13.6, so that's very good. Okay. Now at the higher end, we have platinum, which is 21.1. Now there are a couple elements. Iridium, which is the very highest, is 22.6, I believe, or something like that. 22.6, and that's the most dense element that we know of. But platinum is pretty doggone close, and that's one of the reasons why platinum is it's also a very durable metal, and that's why a lot of times people have platinum rings and so forth. But it's one of the more dense materials on Earth. All right. Now, that is basically density. We will also use, when we're talking about fluids, something that's known as weight density. All right. And weight density is very similar, except for instead of the mass divided by volume, we take the weight divided by volume. And if you remember, weight is just mass times g, which is the acceleration due to gravity, which is 10. And basically we just know that this then would be measured instead of grams, we measure it in newtons, or if it was an English system, we do pounds. But it's going to be newtons divided by the volume, so it'd be like newtons per milliliters. But basically it's the same principle. The more something weighs compared to how much space it takes up, that would be considered the weight density. Now, a related thing compared to density is the idea of pressure. Okay, and pressure is the amount of force divided by the amount of area it's spread over. So, for example, the amount of force that a book weighs is going to be the same regardless of whether it's laying on its side or whether it's standing up on end. The force would basically be the newtons, which would be the weight. So the mass of the book times the force of gravity or acceleration due to gravity times 10 would give you the amount of newtons. And it has the same force if it's laying on its side or if it's sitting up on top. But this would feel different to the force that's exerted on the desk. Why? Because here it's spread out over a bigger area. And so we would say the area is bigger, so this one would put less pressure on the table. When you stand it up on its end, now the same amount of weight or force is on a much smaller area. So if this number is smaller, then that has a greater pressure. A practical example of this, if you were laying on the ground, would you rather, let's just say a 100-pound woman walks on you wearing flat shoes, or that she walks over you with stiletto heels, okay, high heel shoes? Well, technically the woman weighs 100 pounds either way, so the same amount of force is pushing down on you. But if she has flat shoes, it's spread over a wide area, okay? Whereas if she has the heels, that same 100 pounds is into the back heel may only be less than 1 square inch. And so all that force is put in that one little area, puts a lot of pressure, and it would be very painful. Okay, and so and that's also right. That's that's the difference in how it would feel, because you would have much greater pressure when the same 100 pounds is concentrated into a very small area. Now, in a liquid, we say that the pressure is equal to two things that are affected, and one is the weight density, remember the weight compared to how much volume it takes up, and the depth. So if you're doing different liquids, they might have a different density. If you're trying, for example, to talk about mercury, which is a liquid metal, okay, but it's a liquid at room temperature. If you were in a pool full of metal, there would be much higher pressure because mercury is much more dense than water. Okay, if you were in an alcohol swimming pool full of ethyl alcohol, it's less dense, so it would put less pressure on you if you were swimming underneath the water. Okay, but for most times this does not change because the most common liquid that we're usually talking about is water. So unless you're changing the liquid, the weight density is not going to change too much. Okay, so the main thing a lot of times when we're talking about water pressure, when we're talking about the depth. So the deeper, how deep are you in the water? The deeper you are, there's more water above you and the pressure pushes down on you. So pressure in a liquid is due to the density of the liquid, the weight density, but also how much of it is there above you. So if you're walking down the street, you have a fluid above you, which is the air. So it's the pressure of the air, which is basically the weight of the air pushing down on you. If you're underwater, it would be the water above you pushing down on you, and the air, the weight of the air that's above you pushing down also. Okay, so the fluid pressure would be the water above you and the air above you, because those would both add together. Okay, we don't think about us living in an ocean of air, but there is this mass of air above us and it's pushing down. Now, since air is not very dense and it's very spread out, takes up a lot of volume, we don't feel a lot of pressure, or we don't think about the pressure any more than the fish in the ocean thinks about the pressure, because it's used to the water pushing down on it all the time. Well, we're used to the air pushing down on us, but it actually, for every square inch, is about 15 pounds of pressure pushing down on us. But we're used to it, so we don't really think about it very much. Alright, so if we were talking about, for example, the pressure in our ears as we go underwater, it would really depend upon the depth that we're going to. It does not depend upon the volume of the water. Alright, so for example, if you were here in this water and you're very large, you're at the ocean and you're out where it's 3 meters deep and you're sitting right here, whereas if you were in a small pond but it's 6 meters deep, you would feel twice the pressure on your ear over here because you're twice as deep in the liquid. Yes, you're in the whole ocean out here, but you're only 3 meters deep. It's only the depth of the water above you that affects the pressure on you. And we'll talk more about this in part 2.